So let's start today's class. Today we're gonna work on RNN, GRU, and sequence-to-sequence models. And first of all, we're gonna have a lab session on implementing recurrent neural networks using a single cell and using the neural network PyTorch library. And we're also gonna use GRU, which is very similar in terms of implementation. And then we're going to implement the sequence-to-sequence model with attention. And this requires both the encoder, decoder, and the attention. So first of all, make sure that your runtime type is on GPU. And you can run this code to import the required packages. Okay, and we're going to first implement a single RNN cell, and this is the equation for the RNN. So at time step t, we have our input state, hidden state, ht minus 1, and the input t, and we're going to add these after multiplying these with linear matrices, and then we're going to put this at into a nonlinear function such as tan h. And then after we get this hidden output at time step t, we multiply it with v, this matrix, and this output O would be gone through the softmax. So first of all, you guys need to implement this RNN cell, and you need to implement W, U, V, and this forward function. So I'll give you 5 minutes. And when implementing, you guys can look at this code over here, because this is the code we're going to run. So you need to match this implementation with your RNN cell. So please begin. You can use nn.linear for W, U, and V. You should use nn.linear for this implementation. WUV. So this is the code you guys should have implemented, and it's exactly the same as this equation over here. We have WUV, where W is multiplied by the hidden state. So we take the hidden size and also output the hidden size because we want to generate HT over here using A. And for U, we multiply this with the input, so we take the input size as input. We take the input size, and for V, this is multiplied with the hidden state T, so it's hidden size, and the output shape is output size over here. So if we put this into our forward function, it's W times H, which generates a size of hidden size. And then we add this to U times X, which also generates a tensor of hidden size. And then this H is put through, we put this through tan H, and this H is put through V, and we get the softmax. We return the softmax. So you can try running this RNN code. And we have our example here where X is input, H is the hidden state, and RNN should be the output of RNN cell. So if you run this code, you can see that the output shape is 1 times hidden size. One times hidden size for this hidden shape, and for this output shape, it's 1 times output size, which is 4 and 4. So if you want to put RNNs into, if you want to put a sequence into RNN, you actually need to run a for loop, because this RNN cell does not do any for looping and passing through each sequence. So that's when we use the PyTorch library, because the PyTorch library automatically computes the for loop for us. So the entire sequence is put through the RNNs. And below here, we're going to use the PyTorch RNN library. So for the parameters, we have input size, hidden size, number of layers, which is the number of how many RNN layers we're going to stack, and bidirectional. If you set to true, you can implement the bidirectional RNN. And the input and H0 is here too. So this is the code using nn.rnn, where input size 3, hidden size 4, and we have 2 number of layers. So you can try running this code. The input X has 5 sequences, and all these 5 points are put into this RNN sequentially. And this is the output of the final output, where all the 5 inputs are sequentially put through. And then for the bidirectional RNN, we can just simply set this bidirectional to true. And if you run this code, you can see that with the same input size, we have 1 times 5 times 153, 153, and 214, 214 here. But the output is 158 and 154. And this is because we're using this bidirectional RNN. So now you're going to try creating your own RNN module, and you can type in this code here based on this code, which we will run using your implemented code. So I'll give you another 5 minutes. Okay, so we need to put bias equals true because we want to add this bias here. And the reason why we put W and U is because we add bias is because it's just an added term, and we normally put both biases as true. And it doesn't matter because it's just a simple added term here. So unless the shape is the same, it's okay to put bias equals true for both W and U. For the for function here, you should use this RNN and also an output fully connected layer. So this is the RNN code. And when you initialize this, when you create an instance of this RNN, you will put in input size, hidden size, output size, num layers, bidirectional. And based on this initialization, you will create an RNN instance, which uses the same input size, the same parameters as you put in. So you can put in your code to create NN.RNN like this. And you can also create an output fully connected layer, which takes the input size times num direction and generates the output size. So for your forward function, you would put in your input and initial hidden state into this RNN, and you would take the output and hidden state. And this output, for this output, you can put it through a fully connected layer. So run this code, and using this RNN class that you've implemented, you can run this RNN code over here with the output. So here we initialized our RNN class. We made an instance of this RNN class using input size of 3 and hidden size 4, output size 2, num layers 1, and bidirectional. And we put in this x of 1 times 4 times 3. And because we put in the fully connected layer, we would get our output size of 2. So for GRU, we can implement GRU using this nn.gru package. And it's almost the same in terms of implementation with RNN above. So you can remember that this GRU unit has 2 states. So you can put in the parameters, input size, hidden size, num layers, bidirectional, batch first, and the input output. The parameters are almost identical to RNN. So for GRU, you have input size 3, hidden size 4, num layers 1. You can run this GRU code and get the output and hidden state. So initially the input shape was 1 times 5 times 3, but the hidden set, but we put it in through this hidden size 4, so we get 1 times 5 times 4. And this is the output of this sequence of 5, all put through the GRUs. Oh, okay, output -1. This is because we're going to use the last output. So we're going to use this last output and put it through this fully connected layer to generate our output. This means that we're just going to use the last one of this RNN output. Now we have GRU with 2 layers, and you can create an instance of GRU over here. And if you put your X and H0 into this GRU, you would get the output and hidden state. So when you run this code, the output is 1 times 5 times 4. And the hidden shape is 2 times 1 times 4. Num layers, this just stacks. This just means the number of layers of GRUs you would stack. And there would be one hidden state, even though there is 2 number of layers. This bidirectional GRU is also very identical to the bidirectional RNN, and the code is almost the same. So you have your input X and your initial H0. You put it through GRU with bidirectional equals true. And then you can get your output and hidden state. And as you can see, the output shape is twice as long compared to the non-bidirectional one. And now you can implement this GRU module. I'll give you 5 minutes. Oh, okay, for the RNN. I'll paste the RNN code in the chat box. You can refer to it for implementing GRU. If you get this one positional argument error, you should make sure that the init takes in, so when the init takes in 6, you need to initialize this RNN with all these initialization parameters that you put into this def init function. So this is the GRU code, and you first need to define an initialization function where you take in the input, hidden, output, num layers bidirectional, and these are used for nn.gru. So when you create an nn.gru instance, you would put in these parameters, and you would also take the output function where you need to set the hidden size times num layers as input size, and the output size is output size. So for the forward function, you take in this input X and the hidden state, and the output with this output, you take in the last cell and you put it into this output fully connected layer. So when you run your GRU, it's input size 3, 4, 1, and you get your output like this. This is the same as the RNN above. And now we're gonna work on padding. So normally you can use a built-in package for this padding, but in this example, we're gonna try to implement the padding ourselves. So first, import these packages, and you need to download this data set, which is IMDb. If you download it, you can see this review and sentiment. So this is a movie review. And for pre-processing, I'm just gonna go through it quickly. We're first gonna put it into lowercase. We're gonna modify all these reviews into lowercase and create a list of these reviews and these sentiments. And now we need to map each vocabulary into an integer. So that's how we're gonna tokenize this review by creating a vocabulary dictionary. So we're gonna take in all the words in these reviews, and we're gonna create a vocab to integer dictionary. And if you run the code, you can see the number of reviews are 500, and the vocab to int is the dictionary that maps each vocabulary to an integer. You can also encode the labels, so positive and negative into 1 and 0. And for this code, it's a list of all of these reviews here, where each review is expressed into integers. So it's a list of reviews where each word is an integer. And now you can implement this pad features function here, where when this is the maximum sequence length you want to cut off, when you need to loop through all the reviews in reviews int, and you need to generate the padding or the cutoff based on the sequence length. For the hidden shape here, it's actually not related to batch first true, but it's because our H0 is 214. So for pad features, you can get this function where this is the list of your reviews and your sequence length. So for each review, so for each list, you can check the length of the review. And if it's smaller than the required sequence length, you need to pad it with zeros. But if it's longer than the required sequence length, you need to cut off the review. So, and this turns this new into an NP array. So for each feature, you can put in your review. And with this code, you can pad your reviews. And now we're gonna try training this code by splitting it into train test using by 8:2 ratio. We're gonna use this data loader from PyTorch. Okay. You can check your data using, you can check this train loader data by putting in next function here. So there was a typo, you should modify it into this. And you get the input size 50 and the sequence length to 200 because we matched all the sequence lengths into 200 using this pad features. So 50 reviews with sequence length 200 and 50 labels. So in the code above, we used GRU and RNN, but now we're using LSTM and the code is the same as the RNN and GRU. So you can take the embeddings of X and put it through the LSTM and put this output through the fully connected layer. Use the last output cell and put it into sigmoid for classification. So for vocab size, we add 1 here because of the padding. And we can create an instance of our LSTM. And with this code, you can try training your code. Okay. And so for each output, because we put it into a sigmoid, we can classify it based on this threshold. And if it's closer to 1, it's positive, and if it's closer to 0, then it's negative. Okay, pad features part. So the code here, for each epoch, we're running through the whole train loader. And when we get our output, we would classify it positive or negative based on 0.5 threshold. And then after training this whole epoch, we're gonna test with our test data for each epoch. And down here, if you keep running this code, you can see the trained output. I'll just interrupt it here. And for this evaluation part, okay, this is because I didn't complete training this sentiment net, but if you guys complete training this code would run, and we're gonna randomly choose a review from this train data, and we're gonna do inference. So you can see that we're just choosing one random train data and putting it into the sentiment net, our trained model, and we're testing whether it's negative or positive. Okay, so padding function. Now we're moving on to sequence model with attention, and we're gonna use this English to French data set. And for this preprocessing, there is actually a lot of code, but basically what it does is we're just gonna use the English and French pairs, which are less than 10, the token length less than 10, and we're gonna eliminate all these we're gonna eliminate these exclamation marks and question marks. And we're gonna create a pair. We're gonna put it into a pair. So this is the French and this is the English. So you can run this pre-processing code. For the encoder, we're using GRU again, and we're gonna put this X into an embedding and put the embedded output into our GRU. Now we want to use attention decoder. So now you guys should implement this attention weights part over here. So what we want to do is we want to apply attention on the encoder outputs and the decoder hidden states. So I'll give you some time to implement this code. Yes, you can add .CUDA to accelerate the training. And for GRUs, this is the GRU code, which you can reference. So this is the code for the attention weights. And the X in the forward function is the decoder input. The hidden is decoder hidden, and encoder outputs. This is the encoder outputs. So for the matrix multiplication, we want to link the decoder hidden to the encoder outputs using these attention weights. So for the hidden 0, the shape is 1 times hidden. And for the attention matrix, it's hidden times hidden. And for the encoder outputs, it's length times hidden size. So, okay, there's a transpose. And this way we can generate the attention weights, which links the decoder hidden to the encoder outputs. And we can use this softmax. And then we put in this attention weights and the encoder outputs, we multiply this with batch multiplication. And this is put through the GRU decoder. Now this is code for training our data. And the blue score is a metric to evaluate our generated output. So it compares the ground truth. So in our case, the ground truth review and the model machine generated review. And it computes how many overlaps there are between the ground truth review and the machine generated review. So you can try training this code. It would take a long time. And you can put in this decoder hidden over here. It uses the encoder hidden. So we first put in our data into the encoder, and we get the encoder outputs for each element. And using this encoder output, we would apply attention with the decoder hidden. And that is done inside this decoder module, like we implemented over here. And when using teacher forcing, even though we generate the decoded output, when we generate the decoded output, we put in the ground truth for the sequences until t-1. So when we're predicting at time t, we're putting in the exact reviews, the ground truth reviews until sequence t-1. But if we're not using teacher forcing, then we're just putting in the model generated outputs until t-1 and predicting the teeth token. So here, the difference between these two codes is that the decoder input is the target tensor, which is the ground truth. And for this decoder input, we're just using the machine generated outputs. So we're using the first hidden state, hidden 0, for the attention. And okay, maybe I'll share with something else. So when you try training for each loop, you will be able to see this blue score. It's how close this blue score is, a metric which measures how close your predicted output is to the ground truth review. So training this code, you can try it on your own. And after you train this code, you can try evaluating. So this is the input, and this is the ground truth output. This is your generated output. It's somewhat similar, and it's a good thing, which means that it's trained moderately. and you can check your blue score over here. And blue score 0, I think it's because the blue score default n-gram is larger than 2 or 3. So we can check using this code here. It just checks for each word what it would be mapped to using attention. And so here you can see that each word is mapped to some French word, which is the closest to this English word based on the model training. So you can try this visualization on your own. Okay, so this is the end of the class, and we would upload the solution files on Classroom. So today we worked on RNN's GRUs, and for the Torch NN package, we can go through the whole sequence of the input data. And the GRU, LSTM, RNN, their implementation is very similar, so you can reference the RNN code. And when you apply attention to sequence model, you're trying to link the decoder hidden with the encoder outputs. So you're building, you're training you're putting in the attention for the two. And you can also try this training and the visualization on your own. Okay. Do you have any final questions? Okay, I think we can end our class here. Thank you for your participation and see you next week.